Alright guys, welcome to my first ever video on engineering. I'm basically learning it with you guys. Every week I'll post everything I learned the week that just came. And hopefully I do everything accurately. I don't want to lead you guys astray. So the first thing we're going to talk about is current, which is the rate of flow of charge. This is basically A-level stuff. You know how it works. It basically just, if you look at the formula, it basically just means how many coulombs of charge pass per second. That's essentially what current is. So we're going to push past that. I think everyone should know that by now. Next, we're going to look at the different sorts of materials and their electrical properties. Like, first of all, we'll look at conductors. Conductors are very good at carrying currents. They're very good. And the reason for that is that they have a lot of free electrons. Free electrons are basically electrons are basically charge carriers. So if you have free electrons, it means they can move from atom to atom. So when an electric field is established across this circuit, the electrons can respond and move from the different terminals. So this basically means that conductors are used in wires so that we can use them to push it around the wire. The second material are insulators, which are the opposite of conductors. They have no free electrons, and the main reason for that is that normally the electrons, even on the very furthest shell, are quite close. So the electrostatic force that keeps the electrons close to a nucleus is very strong compared to the conductors. It could also be caused by the nucleus maybe having a lot of protons. That can really increase the electrostatic force, but you'll see that later when I talk about the electrostatic force and the formula. So we'll get into much more detail about that later on. The third one is semiconductors. Semiconductors can be insulators and conductors depending on temperature and impurities. Sorry guys, I have a bit of a cold. So what does this mean? It means basically that below a certain temperature, all of the electrons are stuck in the valence shell. They're not free like in a conductor. But once the temperature rises high enough, it means that the electron can gain enough energy to leave its orbit and become free. What about impurities? Impurities means, let's say you have a material and you add more chemicals to it. Maybe the chemicals have more electrons. Free electrons, I mean. And maybe the chemicals might also have wait, let me just make this smaller. It's really annoying me. Maybe it binds to the semiconductor in a way that causes more electrons to be freed. So it can free electrons in a way. So basically, depending on how high the temperature is and what sort of impurity you're using, it can actually work so that it can become a conductor. But below this temperature and with no impurities, it will just mean that it's an insulator. Alright, that's everything you need to know. Second part you need to know about, you know what, I think the thick writing kind of grew on me. I'm going to go back to it. I don't know what it is about it, but I quite miss it. I miss it quite a lot. Anyways, where was I? Alright. The second part you need to know about are electrostatic forces. I was telling you I was going to tell you about it. The formula is Q1, Q2, all over 4 pi epsilon naught r squared. So Q1 and Q2 are the two charge carriers. And the first thing you should know is that like forces will always repel, and unlike forces will always attract each other. So that's the first rule. So if you fill this in and you get, let's say, a negative force, then they will be attracting each other. But if you get a positive force, it will just mean that they're repelling each other. But the magnitude will always be the same in this formula, no matter if you're minusing or using a negative charge or a positive charge, nothing will change. So, oh yeah, we also need to talk about what this means. What is epsilon naught? Epsilon naught is the permittivity of free space. Is it two T's? I don't know. It might be right, I don't know. If it's wrong, just tell me in chat. It's okay. I can take it. So, what does it mean? It basically just means how easily an electric field can be established. Oh, because this epsilon naught is free space, so basically how easily electric field can be established in a vacuum, basically. And the value is actually 8.85 times 10 to the minus 12. So why does it change? Why does the permittivity change in each material? Well, the first thing to know is, sorry guys. For example, let's get an example like water. That's a polar molecule. And that means that positive and negative charges are in two separate sides. So if we pass an electric field in this direction, if we do that, the water molecules will align themselves so that, let's pretend these are the water molecules. They will align themselves. I'm trying to find a new color. Is that all the colors I have? Wait, no. Okay. They'll align themselves so that they face the other way. And this is because, well, we're talking about up here, like forces attract, like forces repel, unlike forces attract. So of course, they're gonna align themselves. So the negative could be attracted to the positive, positive will be attracted to the negative. So it makes sense. But it also means that they form their own electric field in the other direction. And this counteracts the first electric field. So it decreases how much it is. So basically, when we look at permittivity, we said it's how easily electric field can be established. And you can see here, it's less easy to establish an electric field in a polar molecule. But in a vacuum, there's nothing there, so if you put it here, the total electric field, the net electric field, will just be the one that you generated in the first place. So that's basically what it means. So later, I think we're finishing this topic, forces. Just know that that's how it works. And also you can, I think I already told you, but the electrostatic force is what actually keeps the electrons from orbiting each other. So the electrons will not orbit the nucleus, because the nucleus is positive, has lots of protons, and electrons are negative. So they actually attract each other. And you can actually calculate by how much if you use the formula we used up here. Anyways, so next we'll be talking about basically circuits. This is my favorite part of electronics, honestly. Well, so far we haven't really done much. So let's say this is the circuit. Well, this is the battery. In the battery, there are like chemical reactions. And in these chemical reactions, it pushes, sorry guys, my pen is not working properly. Alright, I think it's working now. In these reactions, it pushes electrons from the negative one all the way around the circuit to the positive terminal. So this is the electron. Goes from negative terminal to positive terminal. And when it gets to the positive terminal, it's lost all the energy it's going from the battery. So basically what the battery does, how do I explain this? The battery basically gives energy to the electron when it goes from a low potential to a higher one. And that's actually the EMF. EMF is the energy per Coulomb. Basically, let's say you have an EMF of 12. I think this is easier. I think it's better to explain like this. You try the EMF of 12 volts. You're giving 12 joules per Coulomb to the electrons. And that causes it to go from the positive terminal to the negative terminal where it's pushed out. Because this is low potential, this is high potential. Anyway, so once you have this energy, it's able to basically go from here across the terminal, and it loses energy from the wire because there's resistance. It loses energy in the components as light and heat, and then when it goes all the way back here, it lost all its energy. EMF is used again to give it energy to go back to high potential. So the EMF basically generates the current because it's using the chemical reactions in the battery. It causes there to be little to none electrons in the positive terminal and lots of electrons in the negative terminal. And the EMF does that by giving the electrons energy to be able to jump from one terminal to another. This energy means, let's say this is the battery enlarged. This is very negative, this is very positive. If the electron was here, for example, it will be repelled by this one, and it'll be attracted by this one, so it'll be pushed along the whole wire. So the EMF just basically gives it a push. That's basically what it's doing. It's giving the energy to the electron to be able to go across the whole cell. So yeah, so electrons always go from high potential to low potential. What's next on the list? I just have a list here, guys. Trying to get through all of it. If there's anything you don't understand, yeah, basically. So we already discussed that potential difference is just joules per energy. Per coulomb, sorry. And we have to remember that that's also equal to volts. And we always have to have a reference point. And in graphs, you probably haven't seen this in A level, but if you see this is equal to Earth. Earth is seen as having 0 volts. So when you're comparing something to Earth, how many volts is it above or below 0 volts? So yeah, that's basically what you need to know for potential difference. The difference in potential energy, well, we know here there's lots of energy in the negative terminal because there's lots of electrons there, and of course they're gonna want to leave the negative one and go towards the positive one, and they lose the energy from the EMF that was given to them from the EMF when they go across the components. Even the wire has resistance. That's basically it. Well, because we know this, we can actually write a formula. E equals QV. Anyway, next, I think that's pretty much it. I feel like I'm missing something about it, but I think that's pretty much what you need to know about potential difference, EMF, and all that. It's basically just the energy given per coulomb of electrons, just to give it a shove out the other side. It's basically like a pump, like something like that, you know. So the next part we're going to talk about are resistors, and you have to remember that resistors follow Ohm's law. What is Ohm's law? You probably remember Ohm's law from A level again. It's just when PD directly proportional to the current. But this is a constant temp. So resistors are always they always follow Ohm's law. And because we know that, and we know this is what it starts off with, then we know V equals to Ki. K is actually resistance. And that shows that resistors always have a constant resistance. So yeah, we got Ohm's law. We can write Ohm's law like V equals IR. Second thing you need to know is, well, we need to know about the structures of resistors. Resistors are basically just carbon composites, just like, let's pretend this is it. Resistors are just very poor conductors. So some of them are made of like carbon. Bad. Conductors bad. Bad's plural for some reason. Others are made from like metals, but not like very conductive metals, like maybe like a metal oxide, stuff like that. So there's another formula for resistance. It is where E is area, L is length, P is resistivity, which is just a property of material. It's just literally a property of material, and it can tell you how how much resistance it will have. Every material has a different number. Yeah, that's pretty much it for resistance. Well, we're gonna actually come back to resistance now, because we know that as resistance increases, sorry guys, yeah, as resistance increases, temperature, wait, sorry, I got it the wrong way around. As temperature increases, resistance will increase. And you're probably wondering, why would that happen? Well, when temperature increases, the metal atoms in the circuit, like let's pretend this is zoomed in, they will start to vibrate. And if they vibrate, electrons are more likely to collide and lose some of that energy. And resistance is basically just the opposition to current. How much does it oppose it? So temperature can lead to a greater resistance for that reason. The interesting thing is, well, we already talked about it, but semiconductors, as temperature increases, its resistance will decrease. I already spoke about why at high temperatures some of the electrons be freed, and so the current will increase because there's more charge carriers in the circuit, allowing there to be a higher a higher current. Resistance is another formula. G is the opposite of resistance, it's actually conductance. So how well something can conduct something. This is the formula, 1 over resistance. And it's measured in Siemens. Or you can just measure it in, I guess you can just measure it in ohms. 1 over ohms. I guess you can do that. What else do I have to go through in this lesson? Right, this looks like a good one. The next thing you have to know is resistance in different circuits. If it's in parallel, you can calculate total resistance as 1 over RT equals 1 over R1 plus 1 over R2, all the way to whatever the amount you have. So let's pretend you have 2 ohms, 3 ohms connected to this. You would just have to do 1 over 2 plus 1 over 3. What is that? 6. 3 over 6 plus 2 over 6. 5 over 6. And then you just rotate it, so it'll be 6 over 5. Sorry, I ran out of space. So it'll be 6 over 5 ohms for that. And in series, it's much simpler in series. RT is just equal to R1 plus R2. And if you look at both of them, you can actually tell that in series, it's just adding up the resistances. In parallel, you add up the conductance, as we saw down here. Conductance. You add it up and you just take the reciprocal. That's how you should do it normally. Well, there are more rules if you want to calculate current, and they were invented by a man called Kirchhoff. Here they are. Kirchhoff's. Oh, that's massive. Okay. Kirchhoff's. That just means Kirchhoff's current law. And it means, so the total current entering the oh my god, forget about it again. Just forget about that. The junction Why is it thin again? I liked it when it was big. Okay, let's just increase the brightness. Equals total leaving current. If you guys don't know what that means, let's pretend you have 12 amps going in. And then there's a junction here. Then I1 plus I2 plus I3 would be equal to 12. The 12 equals I1, 2 plus I3. It doesn't have to be shared amongst it equally. It depends on what the resistance in each wire is. It will be shared in the same ratio. And you know that from, what's it called? V equals IR. Basically, yeah. Alright. That's really messy. I hope you can read that, guys. Alright. So the next thing you have to learn about is batteries and internal resistances. What causes the internal resistances? Well, first of all, as you use the battery, as I was talking about before, the EMF is caused by chemical reactions. That's how we get the energy. We use chemical reactions within the battery, and that basically gives the electrons energy. Anyway, we've spoken about that before, but these chemicals are eventually going to have products, and they'll be deposited within the what's it called, between the both of the, this one is the battery inside. It'll be deposited within it, and that would mean when electrons are going from a low potential to a high potential, so when it's going from positive to negative and it gains energy, there'll be some material here that are not conductive. Well, they're not very good conductors, and that will slow the electrons down. They give it less energy to go around the rest of it. So basically, the products of the chemical reactants can cause internal resistance. Our causes are, let's say you have a longer battery. Sorry, I think I'm running out of battery. If it's a longer battery, the electrons take a longer time to get there, and if it's longer, there'll be more resistance along the way. Yeah, there's many more reasons, but I think those are the only two you should be able to know about. Anyways, that's electricity week 1 and 2. I was gonna do it last week, but I was too tired, so I wasn't tired actually, I was just busy. This is week 1 and 2. I think I'll upload some questions that I found difficult, well, not difficult, just different on here. And don't worry guys, I'll do mechanics and materials. I just won't do it today, it's quite late. I have to get to sleep, school tomorrow. So yeah, see you later guys.